Hello students, welcome back to Discrete Mathematical Structure online video classes. So in last class we have seen definitions and theorems. We'll see few more. Okay, so this is about complete graph. So in a complete graph what we are having? Okay, let us see the definition. Complete graph is let V be a set of n vertices. Then complete graph on V is denoted by capital letter K followed by n, that is Kn is where n is representing a number of vertices. Okay, is a loop free directed graph. Okay, where for all a comma b belonging to V and a is not equal to b, there is an edge a comma b. Okay, let us take an example. I'll take n equal to 1. So my vertex set consisting of only one vertex. Since there is a no uh, loops, okay, it should be loop free. So what I'll be getting? We'll be getting only one vertex set. This is next we are having K2. Okay, here there are two vertices. One is A, another one is B. Okay, then A to B, there is a one edge, right? Then we are going to call this one as a complete graph. Now let us take a three vertices A, B, C. We also should have a edge such that A is not equal to B. Means I should not have loop, but A to C it should be there, A to B also connected. All are going to be connected. Similarly, I'll take a four vertices A, B, C, D. Then all of them must and should be connected. A to B is connected, A to C is connected, A to D is connected. Similarly, D to A is connected, D to B is connected, D to C is connected. Like this, B to all are connected and C to all are connected. So what I got is, I got a loop free but all are connected. So I can call this one as K4, this is K3 and this is K2 and this is going to be represent K1. Understood? Next, we are having one more definition, that is complement of a graph G. When we call this one, let G be a loop-free undirected graph on a n vertices. The complement of G, denoted by G bar, is the subgraph of Kn consisting of the n vertices in G and all of the edges that are not in G. Now means which all, it should be consisting of all the edges, whereas then I call that one as K3. If I represent or I take any other edge which is not over here, then we are going to call that one as a complement of G. Okay, so let us take a one more example here is there. If G equal to Kn and G bar is a graph consisting of n vertices and no edges, such as a graph is going to be called as a multi-graph. Let's take an example. Okay, here it is. So what it is consisting of, here is A and B, this is C and this is D, right? So here what I'll be considering, I am going to write this is my graph G, then I'll write a G bar over here. So all vertices must and should be there. So A, D, then B, C, all are here. A to B is there, I'm not writing A to B. A to C is there, I'm not writing that one. A to D, it's there, I'm not writing that one. Whereas D to B, it is not there, I'll draw new one. Then B to C, it is not there, I'll draw that B to C. Then B to, not B, D to C, it is not there, I'll be drawing those things. Okay, so this is going to be called as my G bar. You might be learned this concept in your school also. There we used to do with respect to any subset or set we are having there, we will be considering which is apart from that one. So now we are doing the same thing with respect to graph, right? Next definition we are having is let G1 equal to V1 comma E1 and G2B equal to V2 comma E2 between B2 undirected graph and a function f V1 implies V2 is called a graph isomorphism if there are two conditions. First one A is F is 1 to 1 and onto, and second condition A comma B belonging to vertex set, whereas A comma B belonging to edge set even if and only if F of A and F of B belongs to E2. When such a function exists, G1 and G2 are going to be called as a isomorphic graph. Let us take one example. Okay, so here what is being given, this diagram and this diagram is taken. Yes, here you can see these are written isomorphic, but we'll analyze how it is going to. Look at the diagram. How many vertices are there? A, B, C, D. So I'll be writing for G1. Okay, and here it is W, X, Y, Z. Okay, so these are the vertices that we are having. And you can observe A to B there is a connection. Yes, W to X is also there. If I consider A as W and B as X, then C as Y and D as a Z. If I consider A to B will be W to X. If I consider B to D, then C to Z is there. If I consider D to C, then Z to Y is there. And if I consider A to D, then W to statistic. So hence what I can say is f of A is equal to W, f of B equal to X, C equal to Y, f of D equal to Z. So I can consider, or I can say here is 1 to 1 function, because each of the vertices is representing another set of vertices in the graph G2. Okay, then each of the edges are representing in each of the rest of the edges of this particular G2. So first condition is satisfied and second condition is also going to be satisfied. Understood? Hence these two graph are going to be called as G1 and G2 are isomorphic. Okay, this is a one more example, right? Here if G equal to M equal to R, then G of N equal to S. This is a diagram where M, N, P, Q and R, S, T, U are the diagram representing. Then this I'll represent as C and this I'll represent as D. And here if G of M is R and G of N is S and G of P of G of P is T and G of Q is U, then M comma Q is an H in the 1 to 1 and onto. But what we are having here is H is G of M and G of Q equal to R comma U is not an edge in D. So let us consider H of M equal to S, H of M equal to this S, then H of N equal to R, then H of P equal to U and H of Q equal to this T. Because like this I'm having, here also like this I'm having. Now if I represent, okay, so what I'll be getting, M and N is SR. MP will be having edges SU and MP is ST and NQ is RT, and lastly P and Q is UT. If we consider, we can say that is going to be isomorphic, but if we consider in reverse order, we'll be not getting that one as a isomorphic. Hence C and D are isomorphic in nature. It should be satisfied, it should be mapped one or other way. That is, you have to look which particular vertex is representing what. This is simple, yes, we can see, or else later we can use a paths here or cycles over here and we can find out. So based on this one, there is a um, one more problem is there. Let us solve that one. Let G be an undirected graph with the n vertices if G is isomorphic to its own complement G dash. Such a graph is called as a self-complementary. How many edges must be G have? Let even be the uh, let even be the number of edges in G and E2 be the number of edges G dash for any loop free undirected graph G. We have the number of edges in Kn as G and E1 plus E2 is NC2. Okay, hence G is self complementary. I'll be getting E1 equal to E2, so E1 equal to 1 divided by 2 NC2. If I simplify 1 divided by 2 NC2, if I write that final formula, I'll be getting n into n minus 1 divided by 4. Okay, thank you.